Hey guys, look, new whiteboard. It's really big. Yeah. Anyways, so we'll be doing a discussion about an AP Physics topic. This time it'll be waves, because waves is going to appear on your AP exam in May. What are waves? Well, a wave is a vibration. So a wave is a vibration that is caused by some source. That source can either be an oscillation or a pulse or some sort of propagation that causes it to travel across a medium. What is an example of some waves? So you can have some examples of waves such as electromagnetic waves or sound waves. Now, there are two different types of waves. You can either have a transverse wave, which is like an electromagnetic wave, so label this T, and it looks something like this. Alright? The propagation, right, it travels at a 90-degree angle. Not the propagation. So the wave travels at a 90-degree angle from the propagation or from the source. Right? So you have this vibration that is at this 90-degree angle from this line, which we'll say is the horizontal line that comes from some source. Alright? Now, sound is an example of a longitudinal wave. And a longitudinal wave is essentially a clump of particles traveling across medium. So here's an example, would be like this. You have all these spaced out parts, and then it gets closer together at this part right here. And this part travels across the medium. So like this. And these waves travel, so these waves travel at a 90-degree angle from the propagation. And these waves travel at in the same direction. They travel parallel. And these are perpendicular. Alright? So those are your two types of waves. Let's do some problems involving waves. So we have a transverse wave here between these 2 points like this. Alright, how many wavelengths do you see here? Now, a wavelength is the distance from crest to crest or trough to trough. Now, a crest is sort of like a hill, and a trough is sort of like a valley. So here you have your hills, and here you have your valleys. So how many wavelengths do you see here? Well, let's see. 1, 2, 3, is that it? Now, that cannot be it because we still have this distance here. And this is half of a wavelength. And we have this distance here. And this is also half of a wavelength. So this is 1, and that's 1, and that's 1, right? So we have 1/2, 1, 1, 1, and 1/2. Well, that adds up to 4. 4 wavelengths. And the symbol for wavelength is lambda, which is a Greek letter that looks somewhat like this, which is 4 lambda. Alright? And so what is the relationship between the wavelength and the frequency? So let's define some terms here. So definitions. Right? And so let's give some definitions here. So what is a wavelength? Well, a wavelength is just a measure, all right? is just a measure of the distance from crest to crest, or trough to trough. And now, what is frequency? Now we know from previous units that frequency is related to the period. In fact, frequency is directly proportional to 1 over the period. Right? And so, since we know this, right? So this does not matter here, but we do know that frequency is the number of, we'll say, oscillations in this case, oscillations in 1 second, measured in hertz, and wavelength is measured in meters normally. Now, amplitude is the distance between this line of propagation, okay, and the height, and the top of a crest or the bottom of a trough, all right? And so this is the amplitude, okay? So the amplitude is just the height from the line of propagation. Alright, and so there are your 3 definitions for this unit that you will need to know. You need to know these 3. Now, what happens when you, say, multiply the wavelength and the frequency? Now, before we get to that, let's ask, how do we find the speed of this wave? What is the speed of this wave? Well, speed, we'll say velocity in this case, is measured in meters per second, right? So that means we have to have some unit of distance, or some measure of distance, over some measure of time. Now, we know that distance is in fact wavelength, right? That's the distance, that's the length of the wave, right? And so wavelength in this case would be the distance. And what's our unit of time that we normally use to show how long it takes for something to pass over a certain amount of time? Well, that is the period. So the period in this case is the amount of time it takes for one wavelength, is the amount of time it takes for one, we'll say, a particle, right, on this crest to reach this point right here. So this would be t seconds, in this case, the period, right? So it would take 1 period in order for this point, as it travels across this wave, to reach this point right here, okay? And so this, we can just say that this is just lambda over t. But we know that frequency is also 1 over t. So this is just lambda times the frequency. So in this case, we can just say that velocity is equal to lambda, which is the wavelength, times the frequency, which is f. So like that, we found our definition of velocity based off of this wave. All right, let's do some practice problems involving waves. Now, we had already started off by describing waves and relating them, but now let's do some more problems, like harder problems. We want to challenge ourselves here because we want to prepare for that AP exam. So, in this case, we had a longitudinal wave before, right? So, I'll give you a question here. Right? So here's our line of propagation. So we'll say that this is our source. We'll label it S. Alright, so we have our line of propagation and we have this. How many wavelengths do you see here? Now I see 1, 2, 3, 4. But then we also have half and another half. Alright? So since we have 2 halves and we have 4 here, then we have 5 wavelengths. Now, when I measure wavelengths, I normally measure the distance between 3 zeros. So here you have 1 0, 2 zeros, and 3 zeros. So it's the distance between the first zero and the third zero. Alright, so here we have a wavelength. There are our 5 wavelengths. So this is equal to 5 wavelengths. Alright, so say this distance here has a length of 2.2 meters. Alright, so this length is 2.2 meters and we have 5 wavelengths. Alright, so in that case, since we have 5 wavelengths, right, and we have 2.2 meters, what is lambda? So what is the wavelength? Well, if 2.2 meters is equal to 5 wavelengths, right, then the one wavelength is going to be 1/5 of 2.2 meters, 0.44. Okay. So we found our wavelength. So our wavelength is this. So if this is a sound wave, right, and so the velocity of a sound wave in air, right, is 343 at a room temperature, but the way to calculate that is by doing 331 times the square root of the temperature in Kelvin divided by 373 Kelvin. Alright, so it's just the ratio of this over 0 degrees Celsius, and that's not 373, 273 over 273 Kelvin. Okay, it's just that. Or it's just the temperature in Celsius plus 273 divided by 273. That's it. So, since we have our velocity of sound in air, right? So sound actually doesn't travel in a line. So we know that sound doesn't travel transversely, but we're mapping it transversely. All right? So just because we're mapping it transversely doesn't in fact mean that it travels as a transverse wave. Sound is a longitudinal wave because it's a pressure wave, right? Sound is essentially just the vibration of molecules across a space, which is the reason why sound travels faster when you hit metal rather than when you hit, say, wood, right? You can hear the metal, the sound of the clanging against metal from a further distance than you can wood, right? And also why sound travels faster in water than it does in air, as well as why sound travels faster in solids than it does in either of those two, because the molecules are close together so it can travel further. So it can travel faster because the molecules are close together, and so the pressure wave hits all those molecules. In air, they're all scattered about, and so it takes a while for those molecules to actually hit and cause them to hit other ones and actually travel. But it still happens, which is why you can hear my voice now, because it's being picked up by the microphone on my phone. Alright? So, what we're going to do now is, since we know the velocity at room temperature is 343 meters per second, right, at 20 degrees Celsius, right, which we'll say is about room temperature. So, since we know this and we know the wavelength, what is the frequency of this? Well, we know right? Well, velocity is equal to the wavelength times the frequency. So frequency has to be velocity divided by the wavelength. So this is 343 divided by 0.44, which is going to give you about 667. And so the units here are meters per second, and the units here are meters. So the meters cancel out, the seconds go to the bottom, and we have 1 per second, which is just equal to hertz. Now, I'm not too sure about this value. You can check my answer if you want, but this is just an estimate. But this is the answer here. 343 divided by 0.44. So here we have a problem on the board. So here we have a definition of velocity as it relates to, say, some object, some medium, right? So velocity is equal to the square root of the tension force divided by the linear mass density, which is essentially just the mass of the medium divided by the length of the medium. So this really works well for strings because strings have like a really light mass, but they have a long length. And so here we have a heavy string, it has a huge linear mass density, and here we have a tiny string, so it has a smaller linear mass density. So let's compare the velocities of these two. So which one do you think is going to be larger and which one's going to be smaller? Well, the smaller velocity is going to be the one with a bigger denominator, right? And so since this has a bigger linear mass density, this one's going to have to be larger, so this one is in fact smaller. Okay, and so this one is larger. Now, this wave has a certain frequency from the source. So, how do the frequencies compare here? Well, the frequency stays the same as long as the source stays the same. So, these are the same frequency. Now, what about the wavelength? Well, since this has a larger wavelength than, larger velocity than this has to have, and since they have the same velocity, since they have the same frequency, they have to have a different wavelength. So this wavelength has to be larger, and this one has to be smaller. Why? Well, because that's how this works. Since velocity, right? Velocity is equal to the amplitude times the frequency. If the frequency stays the same and the velocity goes down, one of these has to change, but this one stays the same. So this one has to go down as well in order for the velocity to actually decrease. So now let's discuss what happens as this wave travels across this string. So when it reaches this boundary here, what's it going to do? Well, what it should do is some of it should go onto the spring with the same frequency. Okay? And some of it should bounce back, but on the opposite direction. Why? Because it sees this as a fixed point. This fixed point exists because this has a heavier linear mass density. When a wave reaches a point, reaches a medium, right, or a point at all, of higher linear mass density, then what's going to happen is that the wave is going to come back inverted. But when a wave reaches a point of either like an unfixed end, right, or a lower linear mass density, what it's going to do is it's going to, once it reaches this point, it's just going to come back up in the same direction. So that means that if I draw something like this, right? So we have this wave right here, and we have a fixed point right here. When this wave reaches the next point, what it's going to look like is it's going to look something like this. Why? Because there's destructive interference here. Now, I haven't gotten into the interferences yet, but essentially, constructive interference is when a crest meets a crest or a trough meets a trough, and they combine to make a larger crest or a larger trough. Destructive interference is when a crest meets a trough, and they either make a smaller crest or a smaller trough, or they can cancel out completely if they have the same, or if they have the same amplitude. If they have the same amplitude, then what's going to happen is they're going to cancel out completely, but then afterwards they're just going to travel as they had been before, completely unchanged. So those of you who are in music or are into music and understand harmonics as it relates to music would know that there are multiple types of harmonics depending on the instrument that you play. So say you have an instrument that has two open ends, right? So what does the sound wave look like? Well, it creates a standing wave. Now, a standing wave isn't really standing. It doesn't really look like it's going, like this. right? Right? What a standing wave is really is it's something like this. Right? It feels like it's just going back and forth, back and forth, back and forth here, right? But it's not. What's happening is it's traveling across, but because there's also a fixed end here, right? There's a fixed end on one side, or something on the other side. What happens is that you get destructive interference at points like these, and you get constructive interference at points like this. Okay? And that's the reason why, as it travels across, these points do not move, but these points go back and forth, back and forth, back and forth. So say you have an open tube like this. An open tube like this. So it's going to start off with what are called antinodes. Now an antinode on a wave are points like this. The crests and the troughs. Those are antinodes. On a standing wave, the antinodes are the crests and troughs, and the nodes are the points of destructive interference. So the antinodes are points of constructive interference, and the nodes are points of destructive interference. All right? So here you're going to have two half nodes. Like this. So this is your first harmonic. Now here, the first harmonic, it starts off with, so since you have two fixed ends, it's going to end off with a node. So when you have a fixed end, right, there's going to be a node. When you have a free end, there's going to be an antinode. All right? So here we have two fixed ends. So there's going to be two nodes. So what does the first harmonic look like for this? Well, it looks like this. Boom, done, that's it. One antinode and two nodes. All right? And here we have a fixed end and one open end. One free end and one fixed end. So here we're going to draw our first harmonic here. All right? So this is our first harmonic. Now this one is special because it doesn't really behave the same way as the others, and I'll get to that just right now. So, how do we represent the wavelength for this? So say this has a length of L, and this has the same length, L, and this has some length, L, okay? So this is half of a wave, right? Because there's only one crest here. So the number of waves is equal to half the number of antinodes. Okay, so there's one antinode here, right there, and there's half of one here and half of one here. And there's half of an antinode here, okay, because an antinode has to actually cross. So a complete antinode will look like this. Half of an antinode is this, or this. All right, so here you have, so actually that's a node. Here's your half of an antinode right there. Okay? So the number of waves is half the number of antinodes. Okay? So if you have one antinode, then you have half of a wave. Okay? So here we have half an antinode and a half an antinode, so that makes one antinode. So here we have half of a wave. So that means we have half of a wavelength. And here we also have half of a wavelength. Here we have half of a node, half of an antinode, so we have to divide that by 2. So we have 1/4 of a wavelength. Okay? Well, since we have 1/4 of a wavelength here, 1/2 and 1/2 here, so that's the reason why this one's different, is because it's not actually like the other ones. This one is actually just the same thing. Oh, I forgot to draw the bottom part like this. All right. So here we have half a wavelength, half a wavelength, fourth of a wavelength. So this length is equal to a fourth of a wavelength. Okay? So since the length is a fourth of a wavelength, a half a wavelength, and a half a wavelength, what is the wavelength? Well, that's just the inverse. So for this one, 2 fixed ends and 2 open ends and 2 free ends, you have wavelength is equal to 2L. And for 1 fixed and 1 free, you have wavelength is equal to 4L. Okay, and that's for the first harmonic. So what is the frequency? Well, it has some velocity, right? So this wave has some velocity, right? And what's the wavelength? It's 4L, all right? And here, the frequency is equal to the velocity over what is the wavelength? 2L. And here, our frequency is equal to the velocity over, what's the wavelength? 2L. Okay? Now, the next harmonic, right, is going to be double this frequency, double these frequencies. Why? Why is it double these ones? Well, it's double these because the next harmonic has two antinodes, which means it has one wavelength. Since it has one wavelength, the wavelength is equal to the length. Right? And so that's just 2 times the first frequency. And we call the first frequency the fundamental frequency. And so for these 2 types of waves, the ones with 2 fixed ends or 2 free ends, the frequency of the nth harmonic is equal to n times the fundamental frequency. So in that case, if you are ever given, say, a frequency n and frequency n plus 1, right? Well then, all you need to know is that the difference is that the difference between these two, right? So f of x, we'll say fx minus frequency y, that's just equal to x minus y times the fundamental frequency, right? And so if you know this and you know this, then you can find this. Okay? Now for this one, what's the next harmonic? Is it the second harmonic? Well, can we add half of a node here, half of an antinode here? That wouldn't be possible. The next harmonic is actually the third harmonic. Okay, so for this one, n is equal to 1, 2, 3, 4, etc. For this one, we have, it's the same formula, frequency is equal to n times the fundamental frequency, but in this case, n is equal to 1, 3, 5, 7, and so on. It's only the odd ones. And why is that? Well, because it only can be half because it doesn't have the 2 halves of the antinode. It only has 1/2 of the antinode. So I hope you enjoyed this video on AP Physics waves and you have learned something here, or you have been able to become well prepared for your AP exam.